recording this lecture. The lecture is recording. So, okay, I hope that all of you can hear me, and I will continue our lecture on designing a new computer, Mari computer, that we started from the beginning of the semester to learn different subjects, different knowledge and information to make us enable to design a microprocessor. And because it's the first time I'm trying to connect to invite person to my desktop, I want to make sure that all of you see the presentation screen. So again, one more time, one of you confirm that you see the PowerPoint.
I see it.
Oh, okay, good.
Yep.
Okay, good. So let's see what we have. We have laser pointer, fine, and we can start. Okay, so we talked about the bus, and I said we have two different of bus, point-to-point and multi-point buses. Point-to-point bus, if you see like the laser pointer that I'm showing, the point-to-point buses connect two device or two parts directly to each other, while multi-point buses like are connected between several different devices, and each device can get the control of the bus based on a protocol, and after it's finished like the need to the bus, or when it finished the data transformation, the bus control will be returned to the will be released, and the next device can get the access. Okay, and let me just try to. Okay, that's fine. Okay, and then I started to talk about the clock cycle. I said the clock cycle is important because it synchronizes the like procedure and all the like instructions will be executed in order by using or by getting the like synchronization through the clock cycles. Each clock cycle has a frequency, and the frequency means that how fast the clock cycle is pulsing, and of course the reverse of the frequency is called the period of clock cycle, or of the clock, or the clock cycle. And here I showed the CPU time, and I emphasize that there is a big difference between CPU time and the clock frequency. So higher clock frequency not necessarily means that the better performance. The CPU time consists of several different parameters. Okay, CPU time is equal to seconds per program. How many seconds takes for a program to be executed, and a second per program can be written in the form of how many instructions are per program, and what is the average cycles per instructions, and what is the period of each clock. So any improvement in any of these three parameters can reduce the CPU time, and as a result increase the performance. Any question? So go ahead. You have a question? Okay. So now that we know what is the CPU time, I will tell you like a little introduction about the input and output. Of course, we know that all the computers, all the system, communication systems, they need to communicate with the outside world. If we have a cell phone, we have a like a smartphone with no screen, no microphone, no speaker, there is no point. Well, you know what will be like the what's the point of this cell phone which doesn't have any like a LCD microphone or speaker? Any computer and any communication device needs to have like a method and way to communicate with the outside world, and it happens through the input output system, IO. Okay, IO like means input output. So these IO devices can connect to the CPU through various interfaces. Okay, the interfaces we know what the PCI, like serial port, parallel port, USB, and USB-C, Lightning, and all of those different interfaces are the gate between outside world and like the processor. And the IO has to be mapped. Somehow the processor needs to know which IO it's dealing with. Is it like a printer? It is like a microphone? It is like a touch screen? What is this IO? Each IO has an address. So there is two ways to communicate with IO. The first way is like memory map, which like all the IO devices behaves like main memory. So like a main memory, if you remember, I said that the main memory consists of the different locations from location n up to location 2 to the power of, sorry, from location 0 up to location 2 to the power of n minus 1. Okay, so those are the like locations that we can access through memory. How we can access to those memory using the address bus. If you remember, I said that we have an address bus that carries out, like just carries or transfer the address of memory. And again, if you remember, I mentioned that the any bus consists of three different lines. It was data line, which carries the data, address line, which carries the address, and control line. Okay, so in the first like method, the IO can be like behaves like memory map, and the second one, the IO can be like can behaves like instruction based. As you see in the last line of this slide, it says that we will study IO in detail in chapter 7. So for now, just I'm giving you very short. I gave you a very short introduction of the IO, and then in the chapter 7 we can study this mechanism in detail. Okay, so let's move to the next slide. And now I want to talk about the memory organizations. And I know that I might ask too many times, but I have to make sure that the communication with my desktop works. So I might ask you every few minutes, at least one of you confirm that you hear me.
Yeah, we can hear you.
Okay, good. Because I'm not sure if the like internet connection is like disconnected or no. So like I have to like check with you every 10 minutes to make sure that you have my voice. Okay, so
No.
Okay, good. Let's go to memory organization. Very like important and main concepts for designing a processors. We know that computer memory consists of the linear array of addressable storage cell. Okay, of course, we know how does it work. The problem here I do have, because I don't have my tablet, I cannot just do some figures very good, so I have to use my trackpad. So if we assume this is the memory, it has like n locations, and each location has an address. First location has an address of 0. The last location has an address of 2 to the power of n minus 1. Okay, so the computer memory consists of this linear array of addressable storage cells that are in fact are registers. If you remember, I said that the memory can be built or implemented by the flip-flop. So each address of this memory consists of 8 or 16 flip-flop, D flip-flop, which make 1 byte or 1 word, depending to the size of the memory. So second sentence says that the memory can be byte addressable or word addressable. What does it mean? It means that each location can store 8 bits or 16 bits. If it stores 8 bits, it's byte addressable. When we access to address 0 or address 1 or address 2, we can access to 8 bits of information, which we call it 1 byte. Or it could be word addressable. Word addressable means that each address refers or points to the 16 bits of the information. Any question? Okay. Third sentence is talking about the chipset which are being used to build or make memory. So we know that memory is constructed of a RAM chip. RAM chip stands for Random Access Memory Chip, and they are referred in terms of length times width. What does it mean? Length means that how many addresses are available, how many cells we have, okay? And width means that how many bits are in each cell. So if we assume that in this example, n is, let's say n is 8. If we assume n is 8, of course, 2 to the power of 8, what's 2 to the power of 8? 2 to the power of 8 is 256, okay? 256. So length of this address memory will be 256. And what is the width? Width depends. If it's byte addressable, we say 8. If it is word addressable, we say it is 16. So 256 times 8 means that we have a memory with 256 cells. Each cell has 8 bits. 256 times 16 means that we have 256 cells. Each cell has 16 bits. Okay, so here is a question. If a memory has 256 cells, how many bits we need to identify each cell? Because we have 2 to the power, because we have 256, we know that 2 to the power of 8, 2 to the power of 8 is equal to 256. So by using 8 bits, we are able to address all these 256 locations. So what's the if somebody asks us, okay, if we have a memory with 64 cells, how many address lines we need? Of course, we know that 2 to the power of 6 is 64. So we can say that we need 6 address lines to address 64 cell locations. Any question? Okay. Now that we know how to show and represent a memory, which is a length times width, it's the last sentence shows an example. it says that if the memory word size of a machine is 16-bit, okay, so 16-bit, it means that each cell has 16 bits, 16 D flip-flops. Then a 4 meg times 16 RAM, okay, gives us the 4 megabytes of 16-bit memory. Okay, so can you text me, like, not text, sorry, message me on the text box, chat box, on the chat box, that how many lines, or how many address lines we need to address 4 megabytes. For addressing 4 megabytes, how many like address line do we need? Send answer here. I'm getting different answers. 20. Okay, so still just only 2 of you answered. I need more answers. How many address line I need to be able to address 4 megabytes? Okay, so I got some answers, and unfortunately all of them are wrong. Okay, I got 24, 20, 16, 20, 20, 64. All of them wrong. Okay, but good. Good to I see your names who answered me. It's important for me to see who's trying to answer the questions. Okay, let me give you the answer. Let me give you the answer. 4 meg. What is 4 meg? 4 meg is 2 to power of what number? 1 meg is 2 to the power of 20. 4 meg is 4 times of it, so it is 2 to the power of 2. So 2 to power of 2 times 2 to power of 20 is 2 to the power of 22. So we need 22 address line to address 4 meg memory. Is it clear? Okay, good. So most of you just the answer to the question with number 20. 20 is like needed to address 1 meg, but because it is 4 meg, so we need to have 4 times of 1 meg. So 4 times of like 1 meg. So if 1 meg needs like 2 to the power of 20, and 4 is 2 to the power of 2, and so it is 2 to the power of 22. Okay, so any question? Let's move to the next slide. Okay, here is the answer. Okay, I didn't know that we have the answer in the next slide. So here is the answer. It says that we observe that 4 meg can be expressed as 2 to the power of 2 times 2 to the power of 20, which is 2 to the power of 22 volts. And so we need 22 lines. And the memory locations starts over. If you remember, I said that we always start counting from 0. So we start the first location, first number is 0, first cell, and the last cell is 2 to the power of 22 minus 1. Okay, so the total is 2 to the power of 22, which is 4 meg address. Each address keeps 1 word, 16-bit. Okay, and so here in the last sentence, it says that the memory bus of this system requires at least 22 address lines, which we already discussed. Okay, so and it counts from 0 up to 2 to power of 22 minus 1 in binary, okay? And how we represent information on wire just by having the wire on or off, okay? So we keep the wires on, off, and each wire represent 1 or 0 based on the voltage on it. Any question? Okay. Let's move to the next slide. And here is the other part which we will discuss. We know that the physical memories usually consist of more than one RAM chip. If you have a desktop computer and you open it, you will see that you have 2 or 4 RAM module. Even if you have one RAM module, if you look on the in the RAM module, you see that it itself consists of 8 or 16 RAM chipsets. Okay, so physical memories usually consist of more than one RAM chip. Okay, and why? Because it's more efficient to access to the data if we use more than one memory bank. How? We will see later. First, we have 2 different type of combinations or interconnection between these memory banks. The first one is called low order interleaving. Low order interleaving. First, let's see the definition, and on the next slides we will see some examples. First, let's just focus on the definition. So low order interleaving says that the low order bits means the bits on the right side of a number, a binary number. If we have a binary number 1 0 1 1 1 1, for example 0 0, I'm sorry for this because I have to write with my trackpad, so I don't have my pen. So if we have these 8 bits, the low order bits are these 4 on the right side, and the high order bits are on the left side. Okay, so in low order interleaving, the low order bits on the right side specify which memory bank contains the address of interest. Okay, let's just learn this definition, and then we will see an example. And high order interleaving, in high order interleaving, the high order address bit specifies the memory bank. So just first, let's make sure that we got the point. In low order interleaving, low order bits determines which bank. In high order interleaving, high order address specify the memory bank. Okay, let's see. In examples, we will check in some examples. Okay, here it's an example. It says that suppose we have a memory consisting of 16 2K times 8 chips. So we have 16 chips, 16 memories. Each memory has 2K capacity, and each cell has 8 bits information. What's the total memory? Because it's 16 2K memory, of course, the total memory size will be 32K. 16 times 2K, it's 32K. 32K, how many address lines we need to refer to 32K? Of course, 15. So 15 address lines are needed for each address. 15. Okay. So because we have 16 banks, 16 memory chip, 4 of these 15 bits will be used to select the bank, and the other 11 bits will be used to select the offset in each bank, so the actual address in the bank. Okay, so the total memory was 32K, which needs 15 lines. Because we have 16 banks, we use 4 of these lines to identify or to select the bank, and 11 bits to select the cell in the bank. Let's look in more detail in this example. Here we have the same example, the same memories here. And each address line consists of 15 bits. In high order interleaving, we use this full high order bit to select one of these banks. There are 16, so we use 4 bits to select one of these 15 banks. I got a question. How does 32, how does 32K is equal to 2 to the power of 5 times 2 to the power of 10? It's a question. So we know that the first or second week, I said that 2 to the power of 10 is 1K. And I said 2 to the power of 20 is 1 meg. So we all know that 2 to the power of 10 is 1K. Okay, so it's 1K, and because it's 32K, so we should say 32 times of 1K. So 32, in fact, is 2 to the power of 5. We know that 32 is 2 to the power of 5. 2 times 2 times 2 times 2 times 2 is equal to 32. And so the result will be equal to 2 to the power of 15. Okay, so 32K is 2 to the power of 15. And the other part of the question, how do you know 4 bits are for one thing and 11 are for another? I'm telling you here, the problem just providing us the information. The problem example says that we have 16 bits, 16 cells, 16 banks. In order to select one of the 16 banks, we need, of course, 4 bits, because 2 to the power of 4 is 16. So we need 4 bits to select 16 bank. So we had 15 lines, and 4 of them will be used to select the bank. So the remaining is 11. So as a result, 11 bits will be used to select select the offset. Or is that just a definition? No, it's not definition. As I said, it should be given in the problem. The problem provides all the information for us. The information are provided here: 16, 2K times a bit. All the information we need are here. Okay, so let's continue. So in this example, I was talking about high order interleaving. So because we have 16 banks, we need left high order 4 bits to identify or to select one of these banks, and the 11 bits for the offset. Offset means one of the locations in each bank. Okay, so if we are referring to the first bank, the offset will be select the location in the bank. So why 11 bit? So let's see why 11 bit. What's the size of each bank? Size of each bank is 2K. how many bits we need to like select one to select like one cell from 2k. 2k is 2 to the power of 10 times 2 to the power of 1, 2k. So you see that we need 11 bits to select one cell from each memory, and 11 bits are here. Here, let me just erase the, where is eraser, okay. Okay, so let's go back to the slide and choose a pen. So in low order interleaving, we use low order 4 bits to select one of the memory banks, and we use the other 11 bits to select the offset of the memory location. Okay, so any question? Okay, here is like example in more detail. In this example, before looking to the table, let's just look to the RAM modules here, the RAM modules. How many modules do we have? We have 8 modules. So in order to select one of these 8 modules, how many bits do we need? We need 3 bits, okay? Of course, we need 3 bits to select like this module. And each module has a 4-bit capacity, 4 bit. So how many, not 4 bits, sorry. Each module has 4 cells, 4 memory location. To select one of these 4 memory location, we need 2 bits. So the total address line is 5 bits. So we need 5 bits to address one of these memories. Okay, so if I erase this 3 and 2 and again choose my pen, here we see how does it work. We have 5 bits to address one of these memories, 5 bits. In high order memory interleaving, the high order 3 bits will be used to select one of these modules, okay, and the right 2 bits will be selected one of the location in these memories. Okay, so let's see this table. In this table, we have some decimal addresses. Address 0, 1, 2, 3, 4, 5, 6, 7. If we convert these decimal addresses to binary addresses, we will have these binary numbers. We separate each address, we like to split each address to 2 parts. Left 3 digits and right 2 digits, each address. Okay, left 3 digits, select the memory module, and right 2 digits, select the offset, this location in each memory. So let's see, for the decimal address 0, which module is connected to decimal address 0? It's 0, 0, 0. So module number is 0. Let's go to the next address. In the next address, again, the left 3 bits are 0, 0, 0. So which module is connected? 0. Next address, again 0. Until number 4. When we reach to number 4, the left 3 digits shows the number 1, and it refers to module 1. Number 5, again the module 1. Number 6, again module 1. Number 7 again, module 1. If we go to number 8, we will switch to module 2. Now let's look to the second part of the address. The second part of the address, I said that defines or selects the offset in each module. So for address 0, we are in module 0 and offset 0. Offset 0. If you look to the laser pointer, you will see. In address 1, we are in module 0 and in offset 1, which is shown here. And all these are shown in the in that figure. Let me show you. This one refers to this 0. This one, the module 1. Okay. Number 2 goes to module 1, number 2. Number 3 goes to module 1, number 3. Okay. Now let's move to the next address, which is number 4. If we go to number 4, we see that number 4 is module 1 offset 0. So we access to this point. Number 5 is module 1 address offset 1, which is this address. Number 6 is module 1 third location, and number 7 is module 1 fourth address. And what about number 8? If we had number 8, number 8 would be connected to third module number 2 here. And you see that these numbers, number 8, 9, 10. Okay, let me just make long story short and show the result in these modules. If you look to this module, you can see that addresses 0, 1, 2, 3 are in module 0. Addresses 4, 5, 6, 7 are in module 1. Addresses 8, 9, 10, 11 are module 2, and so on. So if we have 32 addresses and we have 8 modules, and the processor wants to access to address 18. So which module will be accessed? Module 4, because module 4 has the content of address 18. And this one is for high order memory interleaving. And one thing that we should notice is that the neighborhood addresses, like the adjacent addresses, are located in the same module, okay, on the same module. So if we want to access to address 8, 9, 10 at the same time, 8, 9, 10, because all of them are in module 2, it will take 3 clock cycles, because we have to access to address 8, then access to address 9, and then access to address 10, okay? Because all of them are in same module. Let's see how does low order interleaving work, okay? We hope that by using low order interleaving, we can get better performance. This slide shows the low order interleaving. The same story here in the table, but when we splitted the addresses, on the left side, we split it, we just have 2 digits. On the right side, we have 3 digits, okay? And if we look to these addresses, we can see that address 0000 will be stored in module 0. Will be stored in module 0 and offset 0. Okay. Oh, I think this slide is wrong. The same thing I said you because this slide is wrong. I will fix it and talk about it next Tuesday because it says a 0816. Okay, it's not 0123. Okay, that's fine. So here, like the decimal addresses, instead of, let's go back to the previous slide. The decimal addresses were like in sequence 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But in this slide, it shows the decimal addresses in this form 0, 8, 16, 24, 1, 9, 17, 25. And if we convert these addresses to binary addresses, in this column we have binary addresses, and then if we split them, 2 digits on the left, 3 digits on the right. The digits on the right shows the module, so the first 4 data will be stored in module 0. But what are the numbers? What are the addresses? Address 0, address 8, address 16, and address 24. So address 0 will be stored in module 0, offset 0. Address 8 will be stored in module 0, address 1. Address 16 will be stored in module 0, offset 2. Address 24 will be stored in module 0, offset 3. And address 1 will be stored in module 1, address 0. So if we look to these 8 modules, you see that address 0 is in module 0, address 1 is in module 1, address 2 module 2, address 7 in module 7, and address 8 in module 0. Let's compare it with the high order interleaving. In high order interleaving, address 0, 1, 2, 3 were in the same module, but here address 0, 1, 2, 3 are in 4 different modules. Okay, so it's the different type of address interleaving. What's the advantage of this addressing? What's the advantage of low order memory interleaving? Let me explain you. Let's say we have several data bus available, and we want to access to memory locations 8, 9, 10, 11. Because 8, 9, 10, and 11, all of them are in separate chipset, and if we have data buses connected to these modules, we can access all these 4 addresses at the same time because they are in the separate memory module. But if they were in a single memory module, regardless of the available buses, we had to access them one by one. Let's go back to the previous example. If we want to access to 8, 9, 10, 11 in module 2, because all of these addresses are in module 2, there is no way to access them simultaneously. We have to add access to address 8, then address 9, then address 10, and then address 11. But in low order memory interleaving, because address 8, 9, 10, and 11 are located in different memory modules, we can access all of them simultaneously. We can just enable all these 4 memory chips and access the memory at the same time. So it's not a bad idea because we get we gain some performance and speed will be increased. Any question? Okay. And here is one other example on address memory interleaving. Let's see what does it say. It says that suppose we have 128-volt memory. Stop here, just here, right here. 128-volt memory. what does it mean? It means that one, let me change the color. Pen color, yellow, green, red. Okay, it means that the memory is 128 times what? Times 16. Okay, times 16. Okay. At this moment, I have a question, the same question. How many bits, how many address line we need to like select one of these 128 address lines? Again, send me your answers. I hope that I see correct answer. Four answers while I have 20 students. 5, 6. Okay, good. Very good. Most of you gave the correct answer. We need 7 because 2 to the power of 7 is 128. So at this moment, when we reach to this point, we know that the address line is 7 bits. Okay, look here. 7 bits. So we got the point. Address line is 7 bits. And let's look to the rest of the like exam. It says that it is 8-way low order interleaved. 8-way means like 8 memory modules. Low order means that the like low order bits will be used to select the chip. Okay, low order bits will be used to select chips. How many bits? How many of those low orders? Because it is 8 chips, we need 3 out of 7. So 3 out of 7 will be used to select the chipset, and the rest will be used to select the offset. Okay, I hope that it is clear now. So it's the way we can find out these numbers and we can solve the problems. Let me just erase these numbers and say it one more time. Because it is 128 word, we need 7 bits. Because it's 8 ways, it means that there is 8 chipsets. We need 3 bits to select one of those chipsets. There are low order, so the right 3 bits will be selected, will be used to select the module number, and the rest will be used to select offset. Okay, so let's read the rest of the slide. It says, which means it uses 8 memory banks. Of course, we know that. So we use the low order 3 bits to identify the bank, as I mentioned. And because we have 128 words, we need 7 bits, and the 7 bits are here, and the offset will be 4 bits. Any question? Okay. Let's move to the next topic, which is interrupt. Okay, the interrupt is like something which is necessary for any computer device, any like system. And what is the interrupt? Let's say I'm teaching you at the class and somebody knocks the door. So that one is like an interrupt. Okay, let's say you are study your lecture and your phone rings. So it is an interrupt. Interrupt is something that like interrupts the execution of a problem, execution of like a program or any like any like coding and software. So let's see some definitions for the interrupt. It's the normal execution of a program is altered when an event of higher priority occurs. It's very important. What is one example? For example, one of the like higher priority that can occur when you work with your laptop is like you typing some like essay and your battery is like 2%, your laptop battery. So the laptop gets like it gets an interrupt, stops working and save your document, because saving the document helps you to like have it after you connect it to the like power again. So that low battery is an interrupt that interrupts the like execution of a program in a laptop and tells the laptop stop what you are doing and go and save all works, because something gonna happen. The battery is like 1%. So it's like an event. When the event of higher priority occurs, an interrupt will be happen. The CPU is alerted to such an event through an interrupt. Okay, interrupt tells the CPU that okay, there is something that you need to pay attention. Something is like urgent, and there are different type of interrupts. The first type is like the interrupts that can be triggered by IO request. IO request is like let's say coming from IO, like from the printer, from any IO devices connected to the CPU. It can comes from arithmetic errors, like when you divide a number by 0. There is no answer. So an interrupt occurs and tells the processor that, okay, something's wrong. We cannot divide the number by 0. So stop what you're doing and send a message to the user that you cannot do like this calculation, or this like you cannot divide this number by 0. Or when an invalid instruction is encountered. We have different instructions. We have different instructions like add to number, stop to add to number, shift like some data. What if the processor receives an like instruction which is invalid? So it's unknown for the processor. At that moment, an interrupt happens, and the processor goes to like interrupt routines. So let's just review one more time. There are three types of interrupts. First type of interrupts occurs by IO request. So some information comes from the IO and request an interrupt for the processor. Some interrupts are coming from arithmetic errors, like division by 0, and some of them coming from invalid instructions, the instructions that are unknown for a computer. And what is going on after the interrupt? Okay, processor got an interrupt. What it's supposed to do next? Each interrupt is associated with a procedure that directs the action of the CPU when an interrupt occurs. So each interrupt like takes the processor to the procedure or to the part of the program that directs the action of the CPU. Okay, so what you need to do, for example, for a low battery, start to save unsaved works. For division by 0, it sends a message to the user that your calculation is wrong. Okay, and finally, for the interrupt, we have two types of interrupts. We have maskable interrupts and we have non-maskable interrupts. What are those? What are maskable interrupts? Maskable interrupts are the interrupts that we can ignore them. Okay, so I can just tell to the processor that even if the battery is 2%, do your job. Okay, so do your job. Don't worry about the battery, even if it's 2%. So I can interrupt, I can just mask that interrupt. But some interrupts are non-maskable. We cannot just put an order of ignoring those kind of interrupts, like division by 0. If a number is divided by 0, I cannot ask the processor to ignore that, because there is nothing that the processor can handle it. So some interrupts are maskable and some interrupts are non-maskable. And of course, non-maskable interrupts are high priority interrupts that cannot be ignored. But maskable interrupts, they can be ignored. Okay, this was about the interrupts. Any question? Okay, so it's 4:16. I will come back at 4:21 and continue the lecture. Okay, let me just. Okay, so now that we finished the interrupt, I can tell one thing. Everything we learned so far, we can consider them as an introduction to design our own processor. So we learned number systems, we learned gates, combinational circuits, sequential circuits, and the main components of the processor, memory, I/O, interrupts, and now using all these informations that we learned so far, we will start to design our first computer. Not first computer, I would say first super simple processor, CPU. Okay, so our processor name is Mari, or Marie. So we can bring together many of the ideas that we learned so far, and we can use them to make a very simple model computer. Of course, this computer is not a real processor in a real world. It is like a model. It's a machine architecture that is really intuitive and easy. Okay, so it is like a singular purpose which can illustrate basic computer system concepts. Okay, so uh, also this system is very simple. It can give us a deep understanding of like uh, computer systems that helps us to design advanced architectures and more complex systems. So this one, let's consider this processor as a first step to design a complex processor. So first we learn to design the simple processor, and then we will move to the next task, which is designing a more complex processor. First, let's define our processor. Mari processor has some characteristics. What characteristics? First, of course, it works in binary world, and it uses two's complement data representation for negative numbers. So it uses 2's complement. It stores the program in the memory. Each data and instruction, all of them have the same length. So all of them have the same length. They are not like flexible in the length. All of them have the same length. About the memory size of this processor, memory processor, is 4K, and it is word addressable. Okay, it's very important. So we have 4K memory. Each memory cell is a word. It's 2 bytes. Okay. It has 16-bit data words. Okay, and it has 16-bit instruction. Why 16? Because I said that it is word addressable. And from these 16 instructions, from these 16-bit instructions, 4 of them are being used for opcode, and 12 of them are being used for address. We know what is opcode. Opcode is like the instruction, let's say add, subtract, shift, move, jump. Those like are called opcode. So 4 bits, 4 bits are being used for opcode, which define the instruction, and 12 bits for the address. It has 16-bit ALU, which we all know what is ALU. We already discussed it. And it has 7 registers. Okay, registers which are built using D flip-flop. Let's look to this slide in a little more detail. Let me just erase. And let's see. Let's see if we can find some relationship here. How many bits for the address? 12 bits for the address. What's the memory size? 4K. Do we see any relationship between these two numbers? Of course we do. 4K is 2 to the power of 12. So 4K is equal to 2 to the power of 12. So we need 12 bits to address the memory. Why ALU is 16-bit? Because each memory location is 1 word and 16-bit. So data is 16-bit. So ALU should be able to do some processes on those 16 bits. So the size of ALU also should be 16 bits. Now I have a question, and I want to see if any of you can send me the correct answer. Let me open the chat box. Can you tell me? Just send me your answer. I want to see how smart you are. Tell me what's the maximum number of instructions we can have for this processor. For example, for a processor, we have 220 different instructions. What's the maximum number of instructions that we can have for this processor? Any answer? Give me some. Okay, good. Few of you say like 2 to the power of 16. 2 to the power of 16 is like the maximum size of the memory. I'm talking about the maximum number of instructions. Instructions means add, and, or. So those kind of instructions. How many different type of like opcodes we can have? Instruction means opcode. I see a correct answer here. Because we have 4 bits allocated for the opcode, just 4 bits allocated for the opcode, it means that the maximum number of opcodes is 2 to the power of 4, which is 16. So the maximum number of instructions, different instructions, which we can have for this processor is 16 different instructions. Okay, we cannot have and by the way, the answer is here. Okay, so the answer already was here. 16. No, it's not. It's the answer. Okay, sorry. It's the like size of the instructions. Okay, sorry about it. So because we have a 4-bit allocated for the instructions, we can have the maximum of 16 instructions. Is it clear? Okay, and let's move to the next slide. And let's talk about these 7 registers. We have 7 registers that we want to know what do they do. So Murray's 7 registers are, first is called accumulator. Accumulator, which we show with AC, is a 16-bit register that holds a conditional operator or one operand of a 2 operand instructions. Something that unfortunately we have to learn. Accumulator is a 16-bit register that holds the conditional operator or one operand of a 2 operand instructions. We will see in the example, not example, we will see in the next slides that what does it mean. Memory address register, we show it with MAR. It's 12-bit register that holds the memory address of an instruction or operand. Why 12? Because the maximum size of the memory is 12-bit, not the maximum size. The size of memory is 4 meg, which we need 12 bits to like hold the address. So MAR is called memory address register. Okay. Third register is memory buffer register, MBR. MBR is a 16-bit register that holds the data after its retrieval from or before it's placed to the memory. So any data that wants to transfer between CPU and the memory goes to MBR, and from the MBR moves to the destination. So like, let's say memory is source and CPU is destination. Memory sends the instruction to MBR and data to the MBR, and then from the MBR data goes to the processor. Or if vice versa, if the processor wants to write data to the memory, it places the data in MBR, and from MBR it sends the data to the memory. Okay. Okay, so far we learned three different registers: accumulator, memory address register, and memory buffer register. The next one, number 4, is program counter, which we show with PC. It is a 12-bit register that holds the address of the next program instructions. I don't I don't feel that I need to explain it. How does it work? Because we already discussed it, like about the PC, that PC pointing to the next instructions, and when we execute one instruction, we move to the next instructions, and we will fetch that instruction and send the instruction to the memory. So PC is a 12-bit register. Again, why 12-bit, not 16-bit register? Because memory is 4 meg. So what does it do? It holds the address of the next program instructions to be executed. Okay. Register number 5 is instruction register, or IR. What does IR do? It holds an instruction immediately preceding its executions. So each instruction right before executions is stored in IR. And from IR, it goes to the ALU and registers and get executed. Okay, this one is instruction registers. The next register is input register. We show it with INREG, which is 8-bit register that holds data which are being read from input device. And finally, we have output register. Out register is, again, it's 8-bit that holds the data. How many I/O we can have for this processor? Of course, 2 to the power of 8, because I/O registers are 8 bits. Okay, I know it might be like a little confusing for you, just seeing the names and what do they do. But if we go move forward and see the block diagram and see some instructions and study how do they being executed in detail, you will be more confident with these registers. Okay, here is like the architecture of MARE processor. Let me just show you everything in this slide. We have the main memory, okay, which is 4 megabyte. Main memory is connected to MAR. If you remember, MAR was memory address register, which keeps the address. We have input register and output register, which gets the data from input output, sends to ALU. We have IR, which gets the instruction from the memory and send it to to the other part of the processor for the instructions. We have PC, which holds the address of the next instruction, which is supposed to be executed. We have AC accumulator, which holds the conditional instruction or one of the operators, and we have MBR, which holds the data retrieved from the memory. So what is the difference between IR and MBR? IR gets the entire instruction from the memory instruction. Let's say load the address X and add address X with the accumulator. So IR gets the entire instruction, but MBR gets the data, the operands from the memory and store in in it for being executed. Okay, so okay, just let's finish it here, and on Tuesday we will continue on to this and discuss some more instruction in detail, and I'm sure that you will feel better about all this stuff, and you will be very uh, they will become very easy for you all after we see some examples and some instructions in detail. For now, they might seem a little confusing because they were just definitions and labeling and their functionality. But when we discuss them in detail in some with some examples, definitely they will be more they will be easier. Okay, so and one more thing. Uh, that's enough for today regarding the lecture.